Hi, in this video, I'll show you how to use a block cipher. A block cipher is a diagram that is made of blocks, and in this video, I show you some of the most popular ones. So, generically, a block cipher will work this way. So you have for each, so you represent the evolution of the state of your bits as a diagram. And then every time you have n bits coming into a block, then you will have an output of n bits where y1, yn here will depend on the description of the block. Okay, so let's start with one of the perhaps the most famous block, which is the XOR bit by bit. Okay, so the XOR operation on one bit is the operation that takes 1 and 1 and returns 0. And otherwise, everything else behaves like a regular addition. Okay, so 0 plus 1 is 1, and 0 plus 0 is 0. Okay, now this operation on bits can be extended naturally on sequences of n bits. So for example, if you have as input here x1, xn, and y1, yn, then as input, you will have x1 XOR y1, yn XOR xn, okay? Now, this only works, of course, naturally, if you have sequences of the same length as input. Now, a cipher that would be made entirely of this operation would be dubbed a linear cipher. And typically, this doesn't work. This doesn't offer a lot of security. So designers typically try to incorporate nonlinear components in their ciphers, in their block cipher in particular. So let's see one popular choice for a nonlinear component, which is the addition mod 2 to the n. So assume that you have here x1, xn as input, and then say y1, yn. So to make it more convenient, I'm actually going to call that x0, xn minus 1, y0, yn minus 1. Now, this is still a n-bit sequence, but it makes the definition of the number whose binary decomposition is the xi more natural, because I will say x is xn minus 1, 2 to the n minus 1, plus x0, 2 to the 0. Okay, so the number whose decomposition is the xi, and then the same way I can define y to be yn minus 1 to the 2 times 2 to the n minus 1, dot, 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 plus y0, 2 to the 0. Okay, and now as output, what do I do? First, I calculate z, which is x plus y, and since I want it to be over n bits, I reduce this mod 2 to the n. Okay, and then the decomposition z0 zn minus 1 is the output of this particular block. So let's perhaps work it out on an example, okay? So as an example, I'm gonna work on 4 bits because it's really all I'm comfortable doing here on the fly. So let's say you have as input 0 or 1, 0, 0, 1, and for example 1, 1, 0, 1. Okay, so this number in binary is 9, while this number here is 13. Okay, now my number z is 9 plus 13 mod 16. Okay, so that's 22 mod 16, and that's 8. Okay, so what do I have as input? As input, I have the binary decomposition of 8. Okay, so that's so here we are, 4 plus, I think I made a mistake. So it's 6 here, my apologies, and you have the decomposition of 6 here as input. All right, so another way you could have seen this is also by looking at the addition straight up in binary, okay? So you have, for example, 0, 0, 1 and 1, 1, 0, 1. What kind of, so how does that work? Well, 1 plus 1 is a 0, and I have a carry here, okay? And then 0 plus the carry 1 is a 1. Then 0 plus 1 is also a 1. And 1 plus 1 is a 0 plus the carry. And then the reduction mod 2 to the n means that I'm cutting this out, okay? And then my output here is 0, 1, 1, 0. So if you know how to add in binary, then it's even simpler. You don't need to do any kind of modular arithmetic. Now, the next step is, how do we put this all together in a diagram? So here's a pretty simple diagram. Okay, so I'm gonna zoom out a little bit. So for example, let's assume, and that's really to make things simple. I'm going to assume that my key, so my key is going to be, so my message is going to be over 8 bits. Okay, and my key is also going to be over 8 bits. And then I'm going to divide my key into the first 4 bits and the last 4 bits, okay? Now, how do these diagrams typically work? Well, you follow the arrows, okay? So first, say I'm gonna have M0, M1, M2, M3. So my first 4 bits, so that's typical, you know, you take your message and then you break it down into different blocks, and then the blocks will go themselves into different operations, and there's going to be some shuffling, and at the end you hope to get an encryption. So for example, M0, M1, M2, M3, and then I could have, say, M4, M5, and M6, and M7, okay? And then I follow. So, and then I say, okay, this first block goes here, this second block goes here. And then what do? Well, I decide that I want to, for example, XOR. So this diagram will tell me here that the first half of the key would be XORed by this first half of the message. So I could call that, I don't know, like say, K. So now it's terrible because I have a, so K1, 0, K1, 1, K1, 2, K1, 3, okay, and I do the XOR bit by bit, and I get something here that is going to go here to be the right-hand side of the output. And I work out the same here. For example, I get my message, so the second part of my message, and then it goes into this block here, and the result will go here, okay? So that's a typical way to organize a diagram. So this could be, for example, either you could decide, well, this is my block cipher, or you can have a repetition of these rounds, or you could have more rounds after that, right? So that would be a typical way to organize a diagram. Now, a natural question here, of course, would be, how do I decrypt, okay? So each block cipher will have its own decryption method, okay? But typically what you would want to do if it were this particular cipher, you would want to be able to, so given a ciphertext, so let's say C0, C1, C2, C3, and then C4, C5, C6, and C7, you would want to rewind the execution of this block cipher, okay? So those blocks here, so this one and this one, they're not just easy to execute, but we know also how to invert them, okay? So I'm just going to maybe scroll out a little bit. So the inversion of the XOR is really simple because XOR is its own inverse, okay? So the way to invert XOR of, say, Y, I mean, see if you had, for example, I don't know, let's say X was XORed by Z, okay, and to give you Y, and then you want to go on the other direction, then Y would be XORed by X to give you Z, okay? So that's really simple. Now, on the other hand, the the block that it consists of the addition mod 2 is not as easy to invert, because then you have to subtract mod 2, okay? So for example, if you had an x here XORed by a value y to give you the z, okay, mod, so z equals x plus y mod 2 to the n. Then if you want to backtrack, so, you know, maybe y was the key, okay, and you're starting now, you have z and you're trying to work your way back up, then what you have is you have to say y is going to be z minus y mod 2 to the n, okay? So you have a 2 to the n, modulo 2 to the n, and sometimes carries can happen. So remember, when we had, so what would we have before? We had the number 0, sorry, actually, I already forgot what numbers we had. I think the numbers were 0, 1, 1, 0, and then 1, 1, 0, 1. Okay, so this number here was 6, and then this number here was 13, okay? And now you have that 6 minus 13 is minus 7. Now, of course, the answer is not minus 7. You're not going to decompose that. Instead, we're going to reduce this. So minus 7 mod 2 to the n. So here it's 16. And so minus 7 mod 16 is 9. And so we retrieve exactly the 1001 that we had previously. So if you remember when I was demonstrating how to execute this addition mod to the n, okay? So it's slightly more complicated to invert that than the straight up XOR, which is its own inverse, but it's also not the end of the world. Now let's wrap up with a real life example. So apologies for the lengthy scroll here. And so here, this is a real life example. This is the DES, okay? So DES was the standard up until 2001. I mean, when it was replaced in 2001 by a new standard, the AES. So the DES is the standard from NIST, the American standard body. And so, for example, here you have a first round where you have 64 bits of plain text. And the first block, so you see the arrows showing you that it's going through the first block. The first block is a permutation. And then it's split into 2 blocks of 32 bits, a little bit like I was showing with my mock cipher before. And then one block goes into what's called a Feistel function. So the F function that has the key also, and it's not quite the key. It's actually a subkey that is made of 48 bits of the key. I mean, made from the key, and it's 48 bits. And then this output here is 32 bits, and it gets XORed by the first block after the permutation, and then things get shifted like this, and then we repeat, and so on and so forth. Now, what is in this F function? Well, you see first an expansion. So you take 32 bits and in a completely deterministic way, you make 48 bits out of them. And then you have XOR bit by bit. And a very important part here are the S boxes. Okay, so the S boxes, they will take 1, 2, 3, 4, 5, 6 bits. And then there will be a function over 6 bits that outputs 4 bits. And a completely, so obviously the least linear way possible, okay? So this is meant to thwart attacks that exploit linearity of block ciphers. And so these are completely known, they don't depend on the key. But hopefully they will make the cipher nonlinear. And then in the end, you see it goes through another permutation, which is entirely public. So this is just a way to give an example of what things can look in real life. In the course, we're only going to play with mock ciphers in order to demonstrate vulnerabilities. So thank you for your attention. Now you know how to use a block cipher.